There we go. So what we talked about last time is median filtering and Tophat filtering, and in the future, I want to circle back around and start doing some more advanced stuff with filtering. So there's a lot of better filters you can use in very specific situations. One, really important one is the Kuwahara filter, which is a nonlinear median filter, and I can show you how to develop that and utilize that. There's other filters as well, low pass filters, high pass filters. We can look at things that are in the frequency domain, things that are in the spatial domain. There's pros and cons of these different filters. But before we get too in the weeds on any one subject, I want to try to connect everything all together. So a lot of times we're interested in quantifying specific things. So let me pull up G, and so this is our G. So this is green. And this is from my PhD. And you can tell that this is from my PhD because the image quality is really, really low. And honestly, our cameras weren't that great back then. Nor the microscopy hasn't improved too much. Like we've been at the optical limit since the, probably the 70s in terms of glass quality and lens quality and everything. But camera quality has dramatically improved over the last 2 decades. But so this is our image, and basically this is an immunofluorescent stain for a protein called Nesprin-3. And as you can see, Nesprin-3 is mostly localized to the nucleus. You can also see if you kind of squint a little bit, you see how it's enriched on the outer envelope of the nucleus, and less so in the center. You can see that especially here. You have kind of a ring of Nesprin around the nucleus. So Nesprin normally localizes to the nuclear envelope. So that's basically what we're seeing here. Now, one of the things we might be interested in, and what I was interested in during my PhD, is if we do different things to these cells, do they express more Nesprin or do they express less Nesprin? Now, the ultimate answer to this after 5 years of my life is nothing changes the amount of Nesprin. There's always a fixed amount of Nesprin. It never goes up, never goes down, which is sometimes the answer you get in science. But in order to get that answer, I needed to quantify the amount of Nesprin. So we can look at these different, nuclei and say, this one has more Nesprin, this one has less Nesprin, maybe this has some more, this has some more. If I wanted to, I could even open this in Fiji or image J and carefully use my mouse or a tablet to trace a circle around each one of these. And then I could measure the immunofluorescent intensity. And I could do this very, very carefully. And for this image, it would take me 5 minutes. If I had 10 of these images, it would take me 50 minutes. If I had 100 of these images, it would take me 500 minutes. And then as we keep going and adding in, the number of cells, increasing the number of images, this gets painful. So clearly we don't want to do that. We want to use MATLAB to automatically identify the nuclei and segment so we can measure the intensity, the nuclear intensity of all of these different cells automatically. So that's basically what we want to do. So let's build that complete, pipeline, and then we'll go back and talk about, more specifics about different ways to approach problems. So let me also pull up the blue image. And you should be able to see that these are clearly, this is the same field of cells. Here are the nuclei using the nuclear label DAPI. And here's the Nesprin cells using an immunofluorescent stain for Nesprin. And you can see that the nuclei, line up. These are clearly the same cells. And we showed that last time we made RGB, a red, green, blue version of the image. And you could show that the cytoskeleton wraps around the nucleus, Nesprin's in the nucleus, and you could see all the colors all lined up. But in this case, let's say we want to use this image because the nuclei are relatively uniformly bright to segment this image. And this is the kind of concept that a lot of people seem to have trouble with. Like, we're using this as a marker. We're using the nuclear image, we're using the DAPI image as a marker so that we can figure out where the nuclei are, and then we're going to quantify off this image. And the reason why we do this is because segmenting this image is going to be really hard, because this guy's really bright, this one's really dim, this one like barely shows up at all. But if we have a clean nuclear label right here, then we can find the nuclei here, and then we can segment and quantify off of that. So let's go through that process today. So we messed around with a couple of different Tophat filters and a couple of different median filters. So let's just go ahead. I'm going to rerun this code. I want to compare a couple of different C-axis. All right, here we go. So this is our Tophat filter for 1, 2, 3. This is BF2. That's not very useful. This is BF3. And then let's go, let's ignore BF1 for the moment. This is our initial image. And I've adjusted the scaling a little bit here. But basically, you can see in this image, there's this, in our original image, there's this background illumination deviation. Basically, it's brighter in this corner than it is in this corner. That's going to make segmenting hard. So if you look at figure 4, which was one of our Tophat filters, we've removed that background illumination change. Basically, now this corner is just as bright as this corner. These nuclei are still a little bit brighter than these nuclei, but it's not nearly as pronounced as these nuclei being really bright, these ones being really dim. So what we've managed to do with Tophat is flatten the image. We've removed the background noise, and basically the way that worked is a way to think about Tophat is it's a rolling ball filter. We take a ball, we roll it along the bottom of the image, and if there's a bright spot, it will the ball will roll up into that spot. If the bright feature is smaller than the ball we use, so in this case, we used a ball with a radius of 75 pixels, so a diameter of 150 pixels. If the feature is smaller than our ball, it can't roll into the feature and it won't subtract it out. If the feature is larger than the ball, then we subtract the feature out because the ball is just going to follow that feature. So if you look at, again, imagine we have this 150 micron ball. This gentle slope in the background is on the order of hundreds of pixels. So we're going to subtract this large scale feature, this sloping illumination in the background with our rolling ball filter, but we're not going to roll into these individual nuclei and subtract them out because 150 pixels is something like this. So there's no way that ball is going to fit inside that nuclei. Okay, so BF1, BF2 didn't work very well, but BF3 worked pretty well. So I'm going to remove those. So basically our steps are, we have our filter, and then I'm going to call this, so we have BF for our filtered image, and then we have BT for our Tophat image. So median filtering got rid of some of our noise. Tophat filtering got rid of some of our background illumination. So let's go ahead. I'm just going to do BT, and I'm going to delete the rest of this. So now, you just saw this image, but this is the image we're working with now. So now we have this situation. We want to be able to identify these objects without identifying any of this background stuff. So this is really easy for a human to do. Like if I give you a pen and tablet or a mouse, I could park you in front of a computer and you could easily circle this nuclei. And you would know that this is a nuclei, this is a nuclei, and this little fragment right here isn't, and this little fragment right here isn't, and none of this stuff in the background is. But you have to think like a computer. You have to have a set rules for what is and isn't. Now, because the nuclei are so much brighter than the background, the easiest thing to do is set a threshold. Basically, we can convert into a binary image, which is either nuclear or non-nuclear, simply by identifying pixels that are brighter than the background, but dimmer than the nuclei themselves. So I'm going to use this little data tool. And there's some more elegant ways to do this. There's some better ways to do this, some more automated ways to do it as well. And we're going to go through those, in future sessions as we start talking about, more advanced techniques. But for the moment, let's just take a look. So let's go to one of our dim nuclei. So this guy, for example, it's kind of dim. And we have an index of around 97. If I move to a brighter spot, 163, over here it's 95, 100. Now let's go to the background. Maybe 20, somewhere in the tens, in the single digits. So this background, is significantly lower than, our nuclei itself. And, up here in our originally bright corner, again, it's still, in the, it's a little bit brighter than down here still, although it's much, much flatter. But we have, 20, 21, 22, mid-20s. Let's go ahead and then I'm going to throw up the original image just for fun. And let's take a look at that same thing. So we have this nuclei that's kind of dim. We're in the 700s, 600s, and so on. If I go up in this corner, 500, there's a 600 in there as well. Basically, we have a really narrow window between the intensity right here and the intensity right here. But with Tophat filtering, we've eliminated that. Now these values are in, the 10s and 20s, and this value is in the, hundreds, and, maybe as low as 90. So if we want to identify the bright objects from the dim objects, all we have to do is use a logical expression. So I'm going to call this BM for mask. The variables, obviously, you can call whatever you want. And I'm just going to say B greater than, let's say, 75. And I'm picking 75 because it's larger than 20, which is kind of where I saw the background at. And it's smaller than 90, which is kind of where I saw the, nuclei at. And then I'm going to run the script. Oh. I'm going to remove the C-axis because BM is now a logical image. So I screwed up. Everything is 1, and we can verify that. Look at this, 1, 1, 1. Does anybody see the error I made? It was a really silly error. Let's walk through it. So I read in blue. I turn blue, I do median filtering on blue and save it to the variable BF. I take the variable BF, I use a Tophat filter and turn it into BT. And then I go back to my original B because I'm an idiot. So what I really should do here is do BT. So BT is greater than 75. Let's go ahead and run that and see if that works. And look what we got here. So here we have blue or yellow. And again, these are just the colors MATLAB is choosing to render with. They don't have meaning beyond that. But the blue is 0 and yellow is 1. So basically we've gone from this complex grayscale image to a really straightforward, we're either working with something that is nucleus or is not nucleus. Is nucleus, is nucleus, is not nucleus. This nucleus might be dimmer than this nucleus, but at this point it doesn't matter. It's either true or false. This is a logical expression. If anybody has any questions or comments, definitely, jump in at any time. Otherwise, we'll just keep on trucking through this, example. So basically what we've done is we've read in the image, we filtered it, we did a Tophat filter, and then we thresholded the image. Now that we have this thresholded image, what can we do with it? So we can label it. So I'm going to call this BL and BW label. This isn't the most elegant way to do it. I'll show you some other ways, but basically, BW label is something that takes a binary image, which is what BM is. And if you go over to our workspace, you can see that B is a uint16, BT is a uint16, but BM is a logical image. And it's a logical array. It's either true or false. And then let's go ahead and I will run to see what BL is. And this is a label image. And what you can see here, I'm going to bring up the tooltip. Our background is still 0. This guy is 1. This guy's 2. This is 4. This is 3. This one's 17. This one's 22. This guy's 21, et cetera, et cetera, et cetera. So we've converted from a binary image to a label image. Now, what we've done in this case is we've gone from, this grayscale image where the background has a bunch of different intensity values. Each nuclei has a bunch of different intensity values. And now we've blocked. Any pixel that has a value of 8 in the label image is part of nuclei 8. Any pixel that has an index of 15 on the label image is part of nuclei 15. So we've gone from a filtered image to a segmented image, a logical image, and then we've converted that into a label image. And then let's get some information about that. And this is where MATLAB is very convenient. I'm going to use the Regionprops command. And then I'm going to type in Regionprops right here. And for some reason, it takes me forever to open the help file on MATLAB. So I'm just going to let that think for a second and we'll keep on going. But Regionprops is a function that you can use to learn about an image. So, sorry, I wanted to use BL. So basically, the first argument is going to be our label image. And then any other argument is what we want to get out of this image. So for example, I want to get out the area. I want to find out what the area of each nuclei is. And I'm going to suppress output. And I'm going to run that. And then, so I still have my label image right there. Everything's fine. So now we have this S, which is a 23 by 1 structure. And if you look carefully, this little object down in the corner is 23. So we have 23 objects in this image. We have 23 entries into our structure. So structures are a little bit weird in how you address them. Normally you use like parentheses and things like that. I'm just going to type S, which is the name of my structure, in the command window. It's a 23 by 1 structure with the following fields: area. So the way, if I want to figure out what the area of the 15th nuclei is, let's just pick a random number. I do S15 dot area. And this dot indexing is basically unique to structures in MATLAB. It shows up in other programming languages, but in MATLAB, this is a way of indexing structures. Whoops. Sorry about that. So, S15 area, the area of this, 15 is, where was 15? This guy. So this has 7,663 pixels associated with this nuclei. And we could, also figure out what, S14 is, for example. And we can get all of this information, out of this object that we wanted. So that gets us information about this structure. But how do we overlay this structure on our green image? Because what we actually want to do is get information about the intensity of our nuclear image, which, let me go ahead. We want to know what the average intensity of this guy is compared to this guy is, compared to this guy, compared to this guy. So let's go to the help file if it's ever started opening. There we go. And what we have here is a list of different syntaxes that we can use. Now, what we used is this row, where it asks for a label matrix and then the properties we wanted. So let me scoot over a little bit. This is our label matrix, and I won't click. This is our label matrix, and this is the property we want. Now, we could have just fed in BW, where BW is if you read the description, returns measurements for each 8 connected component object in the binary image BW. So BM was our binary image. So we could have just fed in BM, and it automatically would have labeled it for us, basically. But we can go ahead and do the labeling ourselves if we want to. And then we tell it what properties we want. Another way of doing this is we can provide 2 images as an input. So I'm going to click this guy and it will carry me down here. Returns measurements for the set of properties specified by properties. So in this case, it was area for each labeled region in the image I. So it's basically saying you could put in anything here, maybe BW, maybe a label matrix, whatever you want. But then it's going to give you information about I. So let's go down to properties. And then we have, all sorts of things. So we already used area. We can use area. We can, get the bounding box, the centroid, different metrics of circularity or convexity, extrema, et cetera, et cetera, et cetera. And then let's go past these. And we can also, if we, the pixel value measurement properties in the table below are valid only when you specify a grayscale image I. So if we put in a second argument, that's our grayscale image, we can get information like max intensity, mean intensity, pixel values, weighted centroid. So let's go ahead and try that. Mean intensity. And then here, I want to provide, so G is our grayscale image, BL is our label matrix. So what Regionprops is going to do is it's going to use the label matrix we generated from the blue image to assess the mean intensity of specific regions of G. And then I'm going to go ahead and display G. So this is our figure 1. That's our label matrix. This is our green, our grayscale image in green. So let's say I wanted to compare the intensity of this nuclei, which is this guy, and this nuclei, which is this guy. So I would expect this one to have a lower intensity than this one, right? So let's go here and see what our 2 labels are. 7 and 15. So here I want to say S, mean intensity. For 7. So we got a value of 590. So the mean intensity of the 7th nuclei, or that 7th labeled region, is 590. And then the other one I was 15, I believe. And it's, around 1100 or so. And this makes sense. This one's a lot dimmer than this one. This guy's brighter, this one's dimmer. And then let's go ahead and just take a look at the pixel values we see here. So 500, 600, you know, somewhere around there, and we have around 590. So looking at these pixel values ranging from 500s into 600s in some cases, it makes sense that our average value over all of these pixels is going to be around 590. And we can see the same thing here. You know, we have around 1,000, going up to like 1,200. So this 1,100 value makes sense. So what we've done, we filtered the image, we used thresholding to select the bright nuclei, and then we applied those nuclei to create a region of interest so that we could extract numerical information from another image. Is everybody with me so far?
Yep.
So let's say, we wanted to verify that this was actually a good, you know, good fit. I mean, basically, you know, we looked at those two images side to side and they certainly looked reasonable. But let's say we actually wanted to show that. We can use what's known as the Bwboundaries command. So this is, you know, a good way to check your, you know, whether your masked region really lines up, whether your, you know, thresholded region really lines up with your object. So let's say we take, I'm going to call this Bwboundaries of BM. So let's go ahead and run. Oh, I can't reuse B, so I'm going to call this BND. So I executed BND, and BND is a 23 by 1 cell. So you again see this number 23. We had 23 objects. When I ran Bwboundaries, I got a 23 by 1 cell. Let's go ahead and take a look to see what's in BND. So we have, you know, this, each cell is a something by 2 array of numbers. So let's go into, you know, some random one. 962 by 248. What this is, and then 961 by 249, 960, 249. This is the X and Y position of our boundary. So for, this is our fourth object. We have, you know, 4 objects here. This is our fourth object. This is the pixel values tracing an outline around our fourth nuclei. So let's see what this looks like. So I'm going to display image green, and then I'm going to use the hold on command. And what the hold on command is, MATLAB is normally lazy and is going to delete existing data in order to display new data. I'm going to tell it to hold the current data in the figure, and then I'm going to use the plot command, and I'm going to say PND2. Oh, sorry, we were working with 4, weren't we? And let's pick something that shows up well. Let's do R. So I'm going to draw a red line using the plot command, using the pixel values that are in BND4. And let's go ahead and see what that looks like. So 1, 2, 3, 4, and 4 gets traced with a red outline. So basically, this is a list of pixel values, or stored in BND is a list of pixel values, where we can kind of trace around. And let's, you know, go ahead and zoom in. And honestly, this looks pretty decent. You're often going to see a slight shift like this, where it's going to be a little embedded on one side compared to the other. And this has to do with it's a little too tight on this side and a little too loose on this side. This has to do with how the boundary gets resolved when you plot it. So you're always going to see this subtle rightward shift. So I wouldn't worry about that if you see it. But overall, you can see that this really does map the nuclei well. So we can do this, and we can show that this works for 3 as well. We go ahead and run that. Now we've traced our 3rd nuclei. Everything works great. We're pretty convinced that this is working, but it would be great to see this for all of them, right? Let's trace every single nuclei. And this is where the programming comes in. We can certainly change every single value, go from 1 to 2 to 3 to 15, blah, blah, blah. But it would be nice to have MATLAB do that automatically for us. Before we go too far, I want to show what happens when we remove this and we don't have the hold on. This is the traced image, but the image, the grayscale image in the background is gone because MATLAB made the figure, then it displayed the image using image SCG, and then I asked it to plot, and it said, oh, we're doing something else with the plot now, or we're doing something else with the figure now. I'm going to delete what's currently there, and then I'm going to plot something new. If I put the hold on back on, MATLAB knows to keep the image displayed and then plot in addition to what it is. Sure, Shane, what's the question?
So you can cover it now or later, but what if I want to export an image as a JPEG that has all of the nuclei traced, for example?
That's a great question. So let's go ahead and trace all the nuclei, and then I think I'll show you how to export them. I'll show you a couple of different ways, and then I think that would probably be a good place to stop for the night.
Sounds like a plan.
First, show these, do all of these different regions. So I'm going to rearrange the code a little bit. We have these regions right here, or sorry, we have our region props. We're extracting region properties. And then I'm going to put figure right here and image SC. I'm going to delete this guy. So now what we have is I've created a figure, and then I've displayed the image in it, and I've told MATLAB to keep that image there regardless of what else we do. And now what I would like to do is I have Bwboundaries. We can put that back where it was. We have this list of boundaries, and what I want to do is visit each entry in this list. So we have 23 by 1 cells. I want to go to each cell in this list and display the boundaries. And you can see I've used the cell notation here. These are curly braces. So what I've done is curly brace and then an index. So I'm going to the 3rd cell. So the curly braces mean I go inside of a cell. And then inside this cell, if we see, I'm going to go inside 3, and we have a 2-column vector with a bunch of rows. And this notation means I take every row, because the row index is first, and I take the 2nd column, and these are my X values. And then I go to the same cell, so curly brace 3. I take every row of the 1st column, and these are my Y values. I want to point out that our X values are in column 2, and our Y values are in column 1. And I point this out because it might be counterintuitive. Sometimes you might think X is first and Y is second. But if you think about the way, let me pull up an image. Oh, we don't have an image. Let me display one. If you think about this, the columns of the image are vertical. Obviously, they're columns. So X is changing the columns, and Y is changing the rows. And MATLAB always goes rows, then columns. So our X is our 2nd column because it's the 2nd index as far as MATLAB's concerned. So it's just a weird way about thinking about matrices or thinking about images as matrices. Okay, Well, let's actually display every thing, or every boundary. So first, I just want to, let's do something kind of silly. I'll do 5. So this should display 3 and 5. And you can see that's exactly what happened. It circled 3, it circled 5. Now this would be really annoying to do this over and over and over again, right? Like I could manually enter all 23 of these, but that's kind of silly. I can make MATLAB do it for me. So I'm going to create a for loop, and I'm going to create an index. I'm not going to call it I because I don't want people stuck in the concept that they have to call it I. So I'm going to call it cell equals 1 through 23. Actually, let's just do, I'm going to create a vector that's 1, 2, 3, and 15. So what this is going to do is, this is my looping variable cell. Oh, I shouldn't use cell. That's messy. I'm gonna use C. I apologize for the confusion. This is my looping variable C, and C is going to have 4 values: 1, 2, 3, and 15. And what I'm going to do, or what's going to happen, is each time this for loop executes, it's going to go to the first value, then the second value, then the third value, then the fourth value, which means if I change this to C, we should circle 1, 2, 3, and 15. I'm going to run it. And that's exactly what happened. 1, 2, 3, and 15. So let's say we wanted to do 1 through 23. I could either write out this in long form, 1, 2, 3, 4, 5, 6, or I could use colon notation. So I'm going to do 7 through 10, and then 11, just because. And then I go ahead and run this. Again, C is this vector, and each iteration of this loop, it'll visit one of the entries in this vector. So this is going to go from 1 through 6, then 7 through 10 using colon notation, and then 11. And you can see 1, 2, 3, 4, 5, 6, yada, yada, etc. And just to show you what 7 through 10 looks like, 7, 8, 9, 10, using the colon notation. I could also write this as 1 through 23. So 1 colon 23. I'm going to iterate each one. I'm going to go 1, 2, 3, 4, 5, 6. And I don't need the square braces because I'm no longer concatenating. And I've now circled every single object, right? I have, every object circled in my plot. Great. I feel wonderful about that. Well, let's, have some fun. So I can use double colon notation, and I can put a counter between 1 and 23. So I'm going to go from 1 to 23 in steps of 1. This should be the same thing. I should go 1, 2, 3, 4, 5, 6, 7, and that's exactly what I do. I circle all the options again. What if I wanted to only circle every third nuclei? I only circle every third nuclei because my C values, if we just kind of paste this down here, 1, 4, 7, 10, 13, 16, 19, 22. These are the things that we decided to circle. Now, obviously, you wouldn't be using, you would probably just use 1 to 23, but I just want to demonstrate the capacity that you have to control what you loop over. So now I'm going to go from 23 to 1, iterating in steps of -1. And this is just a really inconvenient way of doing 1 to 23, right? We still get everything, but this still works. We don't have to go up when we iterate. We can go down, we can go sideways. It doesn't matter, 23, 22, 21. So let's do this the smart way, 1 through 23. Okay, so this works, we're happy, right? Except we have a problem. Let's say we do another image and there's not 23 objects in the image. Let's say there's 22. Or let's say we adjust our threshold parameters or do some other filtering steps, which we'll talk about in the future. And we remove that little object, and now we have 22 objects. Let's say we don't want to account for any structures that are on the side of the image, and we use a filter to eliminate those, and now we have like 17 objects. So if we were to do those things, we don't want to hard code in 23 here. We want to only list the objects that are actually in the boundaries. So here we can use the length command. So length BND is 23, and you can clearly see that the length of 23 is, or sorry, the length of BND is 23. So we can just put in 1 to length BND. So this should go, because length BND is going to evaluate as 23. When we run this, this goes 1 to 23. We iterate over all the different boundaries. If we had a different number of objects, our boundary cell array would either shrink or grow. We might have 5, we might have 20, we might have 5,000, whatever it is. And we would iterate over a different number of objects. And then you can see that even though we're using, arbitrary length BND, we circle every object that we identify with our system. So I think the last thing, and then I'll let people go to, either enjoy your evening or enjoy your evening at the graduate students networking event, is how do you export this image? Let's say you wanted to save this image. First, I want to change something. I don't like using the Parulia color map. I like using grayscale. So I'm going to change image SC. I'm going to tell it to use a different color map. And I'm going to go ahead and execute that. Weird. So now this is a grayscale image. It's still traced in red. I like this very much. Let's say I wanted to add in a title. So I'm going to go right here and I'm going to add in title, my cool image. Whoops. And you can see that I now have a title on my image. I still have my red lines. And then, what else can we do? That's, probably pretty good. We can add legends and stuff like that. And as we get more advanced, we can talk about how to make these images prettier and better for presentations and better for. Oh, the reason why I like grayscale better, and this is actually a really good question, is because grayscale is linear. A small change, like the increase in intensity between, between 377 and 383 and 359 and 503 is linear with how it's displayed on the screen. So as the image gets brighter, that corresponds linearly to an increase in intensity. If I were to use, on the other hand, a jet color map, oops. Jet is nonlinear, it's multicolor. And also because, let me pull up the color bar right here. Because it shifts from blue to green to yellow to red, this is basically a rainbow. You can end up with really high contrast. So like right here, we go from red to yellow. These really aren't that far apart compared to, this deep blue to this cyan blue kind of thing. So this color map can be misleading. Now, sometimes it's good to have, these kind of high contrast transitions between relatively close values, because it can help you accentuate important parts of the image. But if you're just trying to look at an image and understand it, grayscale gets you a linear brightness increase for a linear increase in intensity, or index. Another common one, and this is the default MATLAB, is Parolia. This color map you might think is like jet, except that it has a very even shift in intensity, so you don't get the really harsh transitions that you get with like jet, for example. But when you're trying to display data, a lot of times you want to mess around with a couple different color maps. MATLAB has several built in. You can actually design your own in MATLAB. And depending on the image you have and the data you want to display, one color map might be better than another. But my default for immunofluorescence data is always going to be grayscale. And the reason why it's always going to be grayscale is because it reinforces that this was a monochrome image, and all of the immunofluorescent images we take are monochrome. Even if the cells are fluorescent green, our camera is monochrome. So grayscale reinforces that we were acquiring a monochrome image to me. And then also you get that linear intensity shift, which means, or a linear correlation between intensity and brightness. So you end up with, a very good perception of what's going on in the image. But that was a good question, thank you. And then let's say we wanted to save this image. So the easiest way to do this is you go to File, and then Save As. There we go. And then you can save it as a figure, which saves it as, a MATLAB figure file, and you can open the figure and mess with it later. A bitmap, a JPEG, etc. So you can save this as a JPEG. And then I'm gonna just put this in MATLAB's fine. So now you can see that this image should have appeared. Huh. Oh, there it is, untitled. So if we open out, you can see it down there. Open outside MATLAB. This will pop up in a second. Really struggling today. Really struggling today. There we go. So we have the image, the figure with the traced objects. So that's one way to do it.
Is there a way to do it where you don't have like the scale and the title on top, and it's just a picture with nothing else but the traced
Sure.
Yeah.
So you remove the title, and now we don't have that. And now, in order to remove the axis, we have to start working with what are known as handle properties. So I'm going to assign HF as a variable, which tells me what the figure is. Everything still works fine. And HF is figure 1. And it has these following properties. Okay. Image SC. And then we can plot on it. But what I'm going to do before that, or actually I'll just do it down here. I'm going to HA equals GCA. GCA is a command that says get current axis. So we're going to figure out what number is associated with our axis. Let's go ahead and run that. And HA is an axis with the following properties. And we have, these various things. We can look at more properties if we want to. But what we can do here is say set HA. So basically, we're referring to the axis. And then, oh man, I might have to go back and double check my values. Xtick location. I'm doing this from memory, so let's see if that works. Let's go to the help file. So I need to know what axis properties we have. So every graphics object has a series of properties associated with it that you can tweak if you would like. So here you can do axis appearance, grid lines, x ticks. Oh, yep, x ticks. So if I set x ticks to an empty vector, really? Yep, there we go. It was x tick, not x ticks. You can see that we still have our y tick labels. We don't have our x tick labels. Because I set the x tick labels to an empty vector, I can also do y tick. And then rather than 0, I'm going to say I want a tick at 400 and 500. And we can see right here, we have a tick at 400, 500. If I don't want this, then I simply set an empty vector. So now we have an image without a title, without axes.
So what does it look like when we save that?
Save as. JPEG. I'm going to write this. And then open outside MATLAB. There we go.
There are. I'd like to talk to you more about this if that's okay, because that ultimately there are still some things about that approach that won't work for my purposes.
Yeah, so you know, that's the whole point of this procedure, is to get people used to thinking through this. We have 5 minutes left, 6 minutes left. What doesn't work? I think I know the answer, but I'm just curious.
I got to go before 6 to get ready. Two things. Thing number one, I can't open, if I want to save a whole image, a whole well, I can't open it all in MATLAB because it uses up too much memory. Thing number two, I don't like how there's a white border around the image.
The white border is super easy to solve, and then there's also another way that we can work around the well image. But let's talk offline or talk next time, so that way everybody can benefit as well. The white border, we basically just adjust the figure size and we adjust the axis size, and we'll get to that eventually. But this is all very doable. These are good questions. Excellent, excellent questions.
Okay. Sounds good. Thank you, Josh.
Yeah. So hopefully everybody, learned something useful. And we're just going to keep going through these things week to week. Does anybody have any questions before we sign off? All right. So I will upload this to the team drive, and hopefully I will see everybody next week, and we can keep building up some of these skills.
All right. See you next week.
Awesome. Thank you.
All right. See everybody next week. And there we go.